far, we had discussed the state postulate, and we said that the states of the system can be defined uh, by two independent intensive properties. All right. Now, once you know that state can be defined by two independent intensive properties, we'll now be moving on towards the understanding of the term process. Process, as it says, that any system undergoes from one equilibrium state to another equilibrium state. That means that the states are changing now. But the process is defined by equilibrium states. One equilibrium state is is changing and a new equilibrium state is being acquired. The process takes place through a path. And how do you define the path? Path is the series of states through which a system undergoes a change. All right. Going from state one to state multiple states in between. So the process is going from one state to another state where both the states are equilibrium. And the path is where multiple states come in between as you move from state one to state two. All these states are equilibrium states. We'll try to have an understanding of this, but before that, how do you define the process completely? Number one, you should have initial and the final states clear to you. Good enough? Then it says that the path it follows should be known to you. And number three, if there is any interaction of the system, which is going from one state to another state, the interactions that take place between the system and the surroundings, that should be clear to you. Clear enough? Now, we'll try to have a look at this definition with respect to this diagram. So, the first thing, this diagram is between property A and property B. Why I have chosen these properties? Because by the state postulate, I know that I need to have two independent properties, two independent intensive properties to define the state equilibrium state of my system. So I have chosen two properties, property A and property B, which are independent and intensive properties. And the coordinates of these properties, property A and B, they define a state for me. So this is an equilibrium state. Similarly, another state, which is state 2, is another equilibrium state defined by property A and property B. The process takes place if I move from state 1 to state 2, but I cannot completely define the process unless I am aware of the process path. Clear? And if there is any interaction between the system and the surroundings, we'll see that in a while. All right. Now, the important thing is, let's say I have this piston with me, piston cylinder configuration with me, and there is some gas stored within the piston. At this or at this moment, I am at state one. Clear? That means the piston, the gas within the piston, which is your system, has certain volume, certain pressure, which defines the state of the system. Let's say I have to move this piston or I have to move this system to a state 2 where the volume and pressure values have changed. That means the property in property B has clear. There are two ways to do it. One is that I apply certain force onto this piston, and the force that I apply is in a very fast manner. I apply a sudden force on the piston. Clear? When I apply a sudden force, what would actually happen would be that the system, the region of the system or the molecules which are close to this piston, they will experience a sudden force onto them. Clear? So over here, there would be a sudden rise in pressure. In this region, the pressure would drastically go up. Whereas in this region of the system, the molecules would effectively be unaware of what has happened at the other end. Clear? since you have applied it in very fast manner, the effect would be transformed to molecules in this region, whereas the far region would essentially be unaware of the pressure change. So would there be a pressure gradient or not? Would there be a pressure gradient within the system or not? इतने खामोश क्यों? होगा नहीं होगा? तो कॉन्फिडेंटली कहो होगा. When there is a pressure gradient within the system, is the system in equilibrium or not? What are the four criterions for the equilibrium? Thermal equilibrium, mechanical equilibrium. What does the mechanical equilibrium say? There should be same pressure throughout the system. There should not be any pressure gradient. That means once the end close to the piston is at higher pressure and the other end is at a lower pressure, your system is not in equilibrium. And therefore, you cannot represent your system on this diagram. Clear? That's a non-equilibrium process that you are doing. The other way to do it is to apply the pressure in a very slow manner. That means throughout this system, the change in pressure is uniform. If you do it in a uniform, if you do it very slowly, the change in pressure would be uniform and there would not be anywhere during the process where you have left the equilibrium. All right. Throughout the system, there would be equilibrium that would be maintained. So you are doing the process in very slow manner. That's how you achieve the equilibrium state too. Clear enough? So the process which is done in such a manner that equilibrium is not disturbed at any time, it is known as quasi-static or quasi-equilibrium process. And in this case, the upper process, which is slow compression, is basically the quasi-static process. And that is the process that you can represent on the diagram or the property diagram. Clear? This fast compression is a non-quasi-equilibrium or non-equilibrium process that cannot be represented on the path because you're not aware that while you are moving from state 1 to state 2, whether your system went through this path, went through this path, or which path it followed, because maybe half of the system was in this region and half of the system was in this region when you had applied sudden pressure. So you are not aware of the exact path the system followed as it moved from state 1 to state 2. Clear enough? All right. Moving on, it says any physical process that you do, it can be represented on process diagrams. Process diagrams are nothing but two independent properties or the two independent property axes that represents the process that is taking place. For example, if I am compressing a gas, that means I have a piston cylinder assembly. I initially have a higher volume and a lower pressure, and I now compress it to a smaller volume and a higher pressure. How to represent it schematically or graphically? You have these property diagrams in which one axis is one of the property, the other axis is the other property. So at state 1, you have a specific volume and the corresponding pressure P1. As you move the system from one state to another state, you have the volume reduced to V2 and simultaneously you have the pressure increased to P2. So even if I don't have this schematic available to me and the diagram is available to me, the direction of process path is given to me, I can fairly realize the physical process that has taken place. Clear? So you would be very frequently using the property diagram or the process diagrams to map the process that has actually taken place. Clear enough? All right. Now, there are certain terms that you should be familiar with. You're already familiar with. These terms basically represent the kind of interaction your system is having with the surroundings. As I mentioned that you should be aware for a process to identify a process, you should be aware of the initial and the final states, the path that has been taken, and the third thing that you should be familiar with is the interaction with the surroundings. One of the interaction could be isothermal. What does isothermal means? Yet that means your system remained say at same temperature throughout the process. That's the isothermal process. That is the kind of interaction you have with the surroundings. Then there is another process or another kind of interaction that you can have in a process, which is isobaric process. What is an isobaric process? And similarly, the isometric or isochoric process where the specific volume remains constant. We define the process or we represent a process to be a cycle when you have performed the process in a way that you started from initial state, moved on to different states and came back to the same initial state. That's a cycle. Clear? Steady flow processes. What do you understand by the term steady flow? Sorry? Same properties. So what's the difference between steady and uniform? That's laminar and turbulent. Anyways, uh, first thing, when I say steady flow processes, that means flow is taking place. Flow means that the system that you're dealing with is an open system or a closed system. Open system, because flow means that there is certain amount of fluid or mass coming into the system. Or so the term steady flow is more often associated with open systems. Clear? And the term steady, the opposite of steady is unsteady or transient flow. But the term steady means that whatever the characteristics of the system, whether it is pressure, temperature, density, mass, energy, they are not changing with respect to time. Steady means that the characteristics of the system or the characteristics of any object is not changing with respect to time. So steady is always associated with time. Let's say I have these control volumes with me. There is mass flowing into the system and mass flowing out of the system. And within the system, I have these temperature distributions. Within my control volume, these are the temperature distributions. At time 1 p.m., if I analyze the system at some other time, let's say 3 p.m., I see that the property of the system, which is temperature, has not changed with respect to time. Clear? So between these times, my system was operating under steady state conditions. That means the characteristics of my system were not changing with respect to time. Clear enough? Now, can I refer to the system at 1 p.m. to be a uniform system? In terms of temperature, is it a uniform system? There are 5 different temperatures at different regions within the system. I cannot claim the system to be a uniform system. The system would have been uniform if there would have been same temperature throughout the system. All right. So although the system is uniform, but between 1 p.m. and 3 p.m., the system is a steady state system. Clear enough? So now you can differentiate between steady state and uniform. All right. Most of the engineering devices which are uh, analyzed as open system, they are basically assumed to be working under steady state conditions. That means it is one of the assumption. So the devices uh, such as turbines, pumps, boilers, condensers, heat exchangers, they are normally they are the open system because mass flow is taking place across the boundaries of the system. But on top of them, another assumption is normally associated with them, that they are working under steady state conditions. This assumption is a very valid assumption under quite a lot of circumstances, and it helps in analyzing the system uh, in a very effective and less cumbersome manner. All right, your analysis becomes very easy with this assumption. So you are assuming this, although your analysis is still quite accurate, but the analysis becomes very easy. Like we assume the value of gravity to be 9.81. If we start taking the actual value of gravity, we would be having trouble finding the value of gravity at specific locations, and that would make our analysis very difficult. Even if we go with the assumption of 9.81 as the gravity value, the analysis would essentially be quite accurate. Clear? This is one of those assumptions that you'll use with open systems when you're analyzing them that makes your analysis easy. However, the analysis is quite correct. Clear? All right. And the bottom line of this steady state assumption is this, that within the control volume, if it is working under steady state conditions, your mass within the control volume remains constant, your energy within the control volume remains constant. So the mass remains same, the energy within the control volume remains same in steady state conditions. Clear? Any doubts with this? All right. Moving on, temperature and the zeroth law of thermodynamics. Any idea about the zeroth law? No idea? All right. Uh, what if I have two bodies at different temperatures and I bring them into contact? What would happen? Sorry? There will be flow of energy and then ultimately they'll lead towards the same temperature. All right. Zeroth law basically says that if two bodies are in thermal equilibrium with a third body, they are also in equilibrium with each other. That means if uh, I place this bottle against the wall and the temperature of these two, say 25 degrees, and then I uh, place this presenter against the wall and the temperature is 25 degrees, that essentially means these two also have 25 degrees centigrade. Clear? Although they have not been in contact. Clear enough? We'll modify it a little, but this is based on the principle where two bodies at different temperatures, when they are brought into contact, they would essentially achieve similar temperature, that is the thermal equilibrium. Clear? This is the same principle on which your thermometers are being designed. जी कुछ कह रहे थे आप? By replacing the third body with a thermometer, the zeroth law can be restated as two bodies in thermal equilibrium are in thermal equilibrium if both have same temperature reading, even if they are not in contact. This is the basis on which your thermometers are being designed. Let's say I have a bucket of ice and water in thermal equilibrium and I place my mercury thermometer within that bucket. Now, when I place it in the bucket, let's say there are no markings on the temperature scale. All right, the thermometer has no markings. Clear? When I place in the bucket of ice and water, the mercury would rise to certain level. It would acquire certain height. Whatever height it acquire, I assign it the value of 0 degrees centigrade. It is me who is assigning that value to be 0 degrees centigrade. That value is nothing. I can assign it 500 degrees centigrade or 500 units. The importance is that the energy stored within that bucket, when it comes in equilibrium with mercury thermometer, they reach thermal equilibrium, and as a result of that, I assign it a certain value, which is 0 degrees centigrade. That is one of the reference point in your thermometers that you use. Clear? In Fahrenheit scale, the same amount of thermal energy is being assigned the value of 22 Fahrenheit. Clear? All right. Now, I have another reference point. That reference point is water and steam in equilibrium. They would have the same amount of thermal energy as ice and water? No, the amount of thermal energy would be different. That amount of thermal energy is basically assigned the value of 100 degrees centigrade in Celsius scale, 212 Fahrenheit in Fahrenheit scale. Clear? So these values are nothing but they are representing the amount of energy stored in a reference point. One reference point is the ice point where ice and water are in equilibrium, and the other reference point is basically steam and water. When they are in equilibrium, the amount of energy stored in that system is basically defined the value of 100 degrees centigrade or 212 Fahrenheit. Clear enough? Then all the values in between 0 and 100 degrees centigrade basically represent certain amount of thermal energy in a linearly increasing manner. Clear? Is this point clear? इसमें किसी को doubt है? All right. So these two reference points are basically used to develop thermometers. Now, there's the same thing written over here that you have two reference point. One is the ice point, the other is the steam point, which you use as the reference point to calibrate your thermometers. In Celsius scale, you assign the value of 0 to ice point, and in Fahrenheit scale, you assign the value of 32 Fahrenheit to the ice point. Similarly, for the steam point, you in Celsius scale, you assign the value of 100 degrees centigrade to the steam point and 212 Fahrenheit to the steam point in Fahrenheit scale. Clear enough? All right. But essentially, uh, these two scales are dependent upon the properties or the thermal energy stored in water or water and ice. अगर मैं आइस को रिप्लेस आइस और वाटर के इक्विलिब्रियम को लेट से मेथनॉल के इक्विलिब्रियम के साथ तो क्या एनर्जी थर्मल एनर्जी उतनी ही होगी नहीं होगी ना दैट मींस these scales are dependent upon the thermodynamic properties of the substance that you are using ideally a thermodynamic temperature scale is a scale which is independent of the properties of the substance clear and the closest we can get is a ideal gas temperature scale which is closely related to the thermodynamic scale temperature scale how is that we'll have a look before that the Kelvin scale is the part of SI scale which is the absolute scale and similarly the Rankine scale is the part of Fahrenheit scale which is against the ideal scale clear enough now let's say I have a container having a gas A and I have a pressure gauge attached to it. Clear? I know by the ideal gas law that temperature is directly proportional to pressure by pressure of a gas if the gas is at low pressure. Clear? Temp Sorry, नहीं clear हुआ? For gases at low temperatures, temperatures are directly proportional to the pressure of the gas. Clear? I'll write up an equation, which is the equation of a linear line, which says temperature is directly proportional to the pressure of a gas if the gas is at low pressure. At high pressures, this equation is not valid. Is it clear? This equation is clear that you have a relationship between temperature and pressure, which is a linear relationship. Now, for a gas A, let's say I bring it close to a container which is having ice point. That means water and ice is in mixture. You have this mixture contained in this box and you brought it in equilibrium with the gas A, which is contained in a container and having low pressure. Would the pressure change? Pressure change होगा या नहीं होगा? Any idea? एक कंटेनर में गैस ए मौजूद है उसका अपना कोई प्रेशर है लेट्स से इट इज एट रूम टेम्परेचर फॉर नाउ द मोमेंट आई ब्रिंग इट क्लोज टू अनदर कंटेनर जिसमें आइस पॉइंट का मिक्सचर मौजूद है दैट मींस यू हैव वाटर एंड आइस क्लोज टुगेदर when they when the container of gas A and the container having the mixture of ice point comes in contact, they would attain thermal equilibrium. Heat transfer would take place. That heat transfer would it affect the pressure of the gas in container A or not? you will have
चलेगा सर.
certain pressure. जी होगा?
होगा सर.
All right, thank you. So uh, you will have a pressure reading on this pressure gauge corresponding to the ice point. Clear? That pressure is known to you, and you will assign the temperature value to be 0 to this point. Clear enough? So now you have a pressure value and a temperature value corresponding to this ice point. Is it clear? Similarly, if I remove this container and somehow bring another container having a mixture of steam point, would the pressure be different or same? Have another pressure value, and I'll assign the temperature for that pressure to be 100 degrees. So now I have two pressure values and two temperature values with me. Clear enough? If I try to plot on a temperature pressure axis the two values, let's say I have 2 points. I have plotted these 2 points. I would only essentially have a single line passing through these 2 points. Clear enough? So any pressure, if I want to measure any other temperature, I would bring this container close to that environment. The pressure would change. I would read the pressure reading, and I would go to this line, and I would read the corresponding temperature to that pressure. That would give me the temperature. Clear? Now, if I change the gas with gas B, some other gas, I have, I essentially have this line for gas A. If I essentially change the gas with some other gas, let's say a gas which is gas B, I will have another line for gas B. Clear? Because the characteristics of the gas would change. So now the pressure readings would change, and you would have a line with a different slope. Is it clear? The remarkable thing with this experiment is that when you keep on changing the gases, when you keep on changing the gases, essentially all of them, when they are extrapolated, they pass through this common point, which is minus 273.15. And if you see what is the pressure at this point, that means on a Kelvin scale, or when you have absolute zero pressure, you basically achieve 0 Kelvin. That is the scale that defines the absolute scale that you have. This value of minus 273.15, it is now independent upon the characteristics of the system that you are using, whether you are using gas A, gas B, gas C or D, whatever gas, this value would remain same for whatever gas you are using. It is independent upon the characteristics of the system. As it was mentioned over here, that a thermodynamic temperature scale is a scale in which properties, the temperature is independent of the properties of the system. This is the point which ideally, or which is closely related to the thermodynamic temperature scale. Clear enough? All right. Now, all of this was essentially for your understanding. There is nothing to memorize in this, but it was for your understanding how these temperature scales are made. For example, if I have the same container and the container says that the pressure in my container is 0, this would correspond to the Kelvin value of 0 and the centigrade value of minus 273.15. Clear enough? All right. Now, the important thing from your point of view is basically the upcoming conversions. You should know that if you want to convert centigrade value into Kelvin value, you have to add 273.15. If you want to convert the Fahrenheit value into Rankine value, you have to add this much amount. You have to convert the Kelvin value to Rankine value, the two absolute scales. This is the conversion. And if you want to convert the centigrade value to Fahrenheit value, this is the conversion. So these four conversions, they should be known to you. Clear? All right. And as it is shown over here, the change in Kelvin would be the same as change in centigrade, and the change in Rankine would be the same as change in Fahrenheit scale, because they are relative terms. Comparison of various magnitudes, it shows the magnitude of different scale, that 1 Kelvin change is 1 centigrade change is approximately equal to 1.8 R or 1.8 F. All right. And then the last point, initially we assumed one of the reference point to be ice point. Later on, this ice point was changed as the reference, and the reference was chosen as the triple point of water. Triple point means where all the three phases coexist. All right. And the value to that state was assigned to be 0.01 degrees centigrade. Clear enough? Is it clear? Why it was changed? Because triple point is more easily reproducible as compared to the ice point. Clear enough? आसानी से आप ऐसा एटमॉस्फेयर क्रिएट कर सकते हैं जिसमें ट्रिपल पॉइंट जनरेट हो जाए. All right, if you're calibrating your system. Moving on to the pressure. What is pressure? Mathematically, what is pressure? Force per unit area. All right. Now, pressure is force per unit area, and the units for pressure Pascal or Newton per meter square. The important thing for you is for gases and liquids, except for the solids. I'll come to solids. For gases and liquids, normally pressures are expressed in various terminologies. You should be familiar with the conversions of these terminologies. Sometimes you hear the word ATM or atmospheric in pressure. Sometimes you heard pound per square inch, which is PSI. Sometimes you hear bar as the unit for the pressure. Sometimes it is kilopascal. There is one another term which is millimeter Hg. I don't know whether you have heard it or not. We'll come to it later on at the end of this lecture, the second half of the lecture. We'll see how this relates to pressure. But these terms, bar, PSI, pascals, Newton per meter square, these are the commonly used terms, and aware of the conversions between these terms. All right. These are the few of the conversions shown, which says that 1 bar, which is relatively very small, is approximately equal to or is equal to zero point 0.1 megapascal or 100 kilopascal. 1 atmospheric is 101,325 pascal or 1.01325 bars, which means bars and atmospheric are roughly the same. All right. kgf per centimeters cube per centimeter square, probably not needed that much, but you should be familiar with Newton per meter square or pascals. You'll be frequently using these conversions. All right. Now, this image shows that two persons having different weights would have different stress on their feet. All right. Depending upon, if I assume that the cross sectional area or the contact area is the same, the amount of force acting is different. What would I say? A person on the extreme right would have more pressure as compared to the person on the left? No. I would refer to it as stress. Normally, in solids, you refer to pressure in terms of stress. This is the difference that I want to highlight, that in liquids and gases, normally you refer to pressure as pressure, but the same units, the same concept in terms of solids is generally referred to as stress. All right. So you say the normal stress acting is greater for one as compared to the other. Clear enough? These are some of the common gauges that you would see, pressure gauges you would see. Just remember that these conversions, the conversions that are shown on the top of the slide, they are essential for you, because at times when you go to market and ask for a gauge, you may not find a gauge for your range in the desired units. For example, I am running an experiment and I want to maintain a pressure of, let's say, 2 bar within my system. I have a nitrogen cylinder on which I can fix up my gauge, and I want to maintain a pressure of 2 bar while I'm doing an experiment. I go to the market and ask for the gauge. The gauge that I have or the gauge that is available for nitrogen cylinder or oxygen cylinder is in PSI. What would I do? छोड़ के आ जाऊंगा. You will bring the gauge. You will be essentially knowing the conversions. The problem comes when you go to the market. Let's say there are gauges. There are various ranges of gauges. I have to maintain a pressure of 2 bar. That means I am in need of a gauge that has the maximum value of 10 bar. उसके यूनिट्स इतनी डिवीजंस हों कि मैं उसको आइडेंटिफाई कर सकूं 2 बार पे. If I go and buy a gauge which has a pressure range of 1 bar to, let's say, 200 bar, it would be very difficult for me to find where the 2 bar lies. Clear? Similarly, if the gauge is in PSI, you should be familiar what range would be suitable for you. Clear? So the conversions become essential when you go to the market or when you're running experiments with the gauges that are different than the experimental requirements. All right? All right. So what we'll do is that I'll stop over here